Well, thank you very much to the FAO for the invitation to share some of our experiences in South Africa and the use of Fenthion and possible alternatives for Red Bull Quelea control. I'm from the Agricultural Research Council and the Plant Health Protection Unit, and I'm in the Pesticide Science and Impact Division. Okay, I'm going to be talking about Quelea. You obviously were well aware about the biology of the Red Bull Quelea. It's estimated that there's 1.5 billion Quelea in Africa, and it is estimated that it's the most numerous bird in the world. They can occur in huge flocks. Here you see pictures of the male Quelea in breeding plumage, and they can have up to 5 breeding attempts per year. The distribution of Quelea occurs right through Africa in 19 countries. There are certain subspecies. The ones that are found in Southern Africa are in Southern Africa, it's Quelea lathmii, and in Eastern Africa, it is Quelea ethiopica, and in the northern parts of sub-Saharan Africa, it's Quelea. And as you can see, it is quite widespread, and Quelea they prefer grass seed, so you'll find them in the savannas, and also those that are littered with thornbush sites, which they prefer to roost in. Okay. In Quelea is probably the most or the worst pest of small grain crops in Africa. As you can see here, this is an example of small grains in Tanzania, and the one spike that is held in the hand shows that almost 50% of the seed is already being predated. This is just a close-up view of the breeding plumages of Quelea. Okay. What I'll be talking about is to look at the environmental fate of Fenthion in the environment, and I'll quickly go over looking at the Quelea, the Fenthion in air and grass and leaf samples and invertebrate samples, and when once Quelea is sprayed, the dead Quelea carcasses, the bird blood, and some results of the pitfall trapping, as well as soil. Right. The chemical can be applied either ground-based in a vehicle like this. This is an example of a Quelea spray operation in Botswana using a ULV method, the AU 8000 spray head. And in this photo, you can see that the people driving in the vehicle, they actually should be equipped with respirators as well to protect them from the highly concentrated plume of pesticide. The area application is done at night, and normally results in a lot of dead Quelea, which by law in South Africa has to be collected by the farmers who have to provide labor to collect the dead carcasses to prevent secondary and tertiary poisoning. Okay. There's a very nice serum and plasma choline esterase tester available that can give you the results within a couple of minutes in the field, and the blood is taken from a finger prick. Okay, if we look at aerial data, as you can see, this is the different heights of the sample at 1 meter, 3 meters, 6 meters, and 10 meter samples, air samples that are collected. So this is high volume air sampling. It runs at 300 liters of air per minute, and the color indicates the sampling intervals from 1.5 hours up to 52 hours after application. So if one looks at Fenthion, you can see that right up to, here's a case, right up to 42 hours after application, there's still significant amounts of airborne pesticide residue in the air. All right, so obviously this also means that because the plume now has the plume of the airborne or volatilized organophosphate, then also moves with the wind, that implies that the area that is covered by the pesticide rapidly expands as well as in high wind, for instance. So we've picked up the pesticide in air up to 3 kilometers downwind from the site. And the one photograph that I've just previously shown, that's why we mount the telescopic sampling masks on vehicles, so that we can continuously position the sampling at downwind from the site. And we use a weather station to get the wind direction. So just before sampling starts, we take the last hour's weighted average of the wind direction and wind speed, and we can radio the coordinates to the vehicle to position itself for the sampling event. South Africa is now using Sahanaphos, and there's also significant concentrations of Sahanaphos. Interestingly, in some of the cases, there's a plume at about 16 to 25 hours after application. So that's normally when the sun comes out, and we see that the heating of the leaf surfaces and the vegetation surfaces actually increases a plume of volatilized pesticide into the air. Okay, if we look at the Fenthion in soil, this is the results that we got from four different sites in South Africa. You can see the results are quite variable, and we get significant concentrations up to 70 days after spraying. And the pesticide registrar in South Africa always sometimes uses European data that is used for the registration process, such as the half-life concentrations in soil, etc. But the soil types of Africa is not compatible or comparable to the soil types in Europe, where pesticides tend to have much shorter half-lives. Okay. If we look at just a second, or degradation in leaves, what we found is that we're taking samples of the trees that have been sprayed at night by the aircraft, and this is the results from 7 sites in different provinces in South Africa. And you can see there's still a risk 14 days after application. So that has the repercussions for livestock. So livestock typically have to be removed from the area for at least 2 weeks after spraying. Okay, there you go. Okay, so if we look at the effect of invertebrates, so those are invertebrates that we collect after application. So we look at the vegetation, etc., and we do transects through the sites, and then collect the vertebrates, and we analyze them for Fenthion content. And as you can see, at 2 weeks after application, there's still a significant amount of pesticide in the invertebrates that we collected. So that'll be grasshoppers or beetles, etc., that have fallen on the ground, and that still provides a risk for secondary poisoning to insectivores. Okay, there you go. Okay, when we're looking at the degradation in Quelea carcasses. So what we do is we collect Quelea carcasses, or we put a wire mesh cage over dead Quelea carcasses to prevent scavengers from reaching them and becoming contaminated. And then we analyze the content of the carcasses over a period to follow the amount of Fenthion still left in the carcasses. And as you can see, even after 70 days after application, the carcasses still have significant amounts of Fenthion in them. And this is also from the 7 sites in different provinces in South Africa. My forward button is a little bit slow. Okay, when we're looking at the levels of Fenthion in bird blood, this is right after application, 3 hours and 12-hour samples of birds after application. We still find very high levels of Fenthion in the blood, and at 2 weeks post control, we still found Quelea floating around that still had relatively high levels of Fenthion. So those are the Quelea that have not had the acute toxicity dose, but they still have high levels of Fenthion in their blood. So that implies that can be the case in more of the non-target birds that are affected by Quelea spraying. Okay, if we're looking at the pitfall sampling, so we did pitfall trapping in different sites. So this is a conglomerate of 3 sites. So these are 3 control sites, and on this axis are the different families of taxa that we have sampled, and the y-axis gives us an indication of the number of individuals per family or per taxonomic taxa. The sampling interval, each sampling intervals were done at 6-week intervals. So we followed the pitfall traps for over 2 years to see what effects there are. So these are the control sites, and what we did notice over a 2-year period is that there were relatively very high numbers at the beginning of the 2-year period, and as the amount there was drought in the areas that we sampled, so there was a gradual decrease in the number of in the number of individuals per taxa that we looked at. So the colors on the screen is the same as for the control sites. Okay, when we look at the spray sites, this is now the first week after sampling, and as you can see over that whole period, there was almost a 90% reduction in the initial stages of a lot of different invertebrate families that we looked at, and at the end of the 2-year period, we only saw recovery of most of the taxa. So the recovery period in the sprayed sites can take an extremely long time to occur. Okay, and as has been alluded to by the previous speaker, who gave a very, very good overview, there is severe effects from organophosphate poisoning, and delayed neurotoxicity can be one of them, and as has been stated, is very toxic to non-target organisms. So if we look at alternatives to pesticide control of Quelea, the alternatives has to have some kind of impact on the sensory physiology of the Quelea. So it can either affect the sight or hearing or smell or taste and touch, or it can have a physical-mechanical effect. And the alternatives can broadly be grouped, categorized into lethal and non-lethal alternatives, and it can be grouped into physical alternative, where trapping and nest harvesting, bird scaring falls under. And then we can look at the other one is looking at physico-chemical actions against the Quelea themselves, like in the instance of repellents and explosions. One of the hearing effects is using propane gas cannons. So these are set to make noise at random intervals to chase the birds away from the crops. So it has been tested in South Africa, and some farmers are still using it, but it is for the huge farms, commercial farm areas, it is counterproductive and not cost effective, because you do see Quelea settling at the center of the cultivated fields. So it's difficult to continuously manage this operation. What we've seen, this is slides from Tanzania, where we have ropes that are latched to the home, and there are little cans with stones in them linked to the person who then pulls it, and it's normally children that are used in order to do this. So when the Quelea get into their crops, the child has to be vigilant and move that to create the sound to chase away the Quelea. So this is a full-time job, and it has some severe consequences for socioeconomic consequences, because it takes the child out of school. So it has effects on education. This is a slide from also from Tanzania, and this is a little boy cracking a whip made from baobab fiber, and it is quite physically intensive work to chase them away. If they don't do that, the plots of half a hectare to 1 hectare can be wiped out in 2 or 3 days. So this is a very, very intensive, tedious job to give to a child. When we're looking at physical-chemical effects, South Africa also employs explosion control actions with the same in Botswana. So the fuel air explosions is normally done by placing explosive charges connected by the detonation cord. So this cord actually explodes simultaneously throughout the site, and canisters with up to 15 liters of fuel is placed on top of them. And when this cord is ignited, it creates the combustion as well as the spreading of the fuel for the fuel air explosions. So in dense areas, up to 400 bombs can be placed per hectare if there's dense bush encroached thickets, and up to 2,000 liters of fuel is used per hectare. So it's very costly, very labor intensive, and it is employed in areas which are very ecologically sensitive and within, say, 400 meters from open water bodies, etc. It results in total habitat destruction. It sterilizes the site. There's no living biodiversity left after such an explosion, and it creates petrochemical pollution as well as the plastic that gets scattered across the environment. We did a trial looking at using chemicals to disrupt the insulation of the Quelea, and to also to decrease the energy budget. So Quelea have to feed every single day to maintain the high metabolic rate. So what we've seen is sometimes the winter temperatures in South Africa could go down to like -4. And we see if we then disrupt the insulation, either with calcium chloride water or with molasses, one can get a reasonable mortality of anything between 30 to 40% of the Quelea. Because of the sites in South Africa is very, very inaccessible as a norm, we looked at applying chemicals through aerial application. Excuse me. And the maximum delivery rate we could get from an aircraft is 165 liters per hectare. So that is almost high volume application akin to their handheld spraying with a knapsack. So although it is practically possible, the cost effectiveness I think is not. The plane will have to replenish the hopper and land and refill quite a number of times for each hectare. So it can be an alternative. We found that anything between 50 and 80% of molasses mixed with water can work, but we needed to the normal application rates for aircraft normally provides about 30 liters per hectare, which is insufficient for the physical coverage of the area and the Quelea themselves. So we modified the aircraft to deliver higher rates. We also tried different booms. Even with big orifices, we couldn't get to more than 60 liters per hectare. So we had a central orifice with veins in it, and that gave us the concentration. So you can see on the leaves, that would be the typical deposition pattern at 165 liters per hectare. Excuse me. Okay, so if we look at explosions, the effect that it has, excuse me, it creates huge craters in the in the ground. Sorry, I have a little cold, so bear with me. Just a second. And this is an example of harvesting in Tanzania. So breeding colonies are used for collecting chicks inside the nest. So that actually reduces the Quelea population going forward in the season. And they are very, very adept at collecting Quelea, which is a very, very good nutritious protein source, and definitely more nutritious on the analysis that we have seen. It's more nutritious than A1 grade beef. So there's much more dense protein and vitamins and minerals per gram than compared to beef. So it's actually one of the most nutritious foods that one can eat. What they typically do in Tanzania is they collect the chicks. That afternoon, they make a fire and they put the chicks into the fire. Once they are cooked, they degut the birds, and the whole bird is consumed. If we're looking at physical methods, carrying on from that, there are different types of traps. This is an example of a trap that we built for Professor Cheek in Tanzania. And this is the example of the trap used in South Africa, built with wire and chicken wire. And this is an example of a woven basket, the Tanzanian trapping basket, and various levels of success has been achieved through this. The reports are from Chad that they are very successful by putting traps on long poles 4 or 5 meters high, and they stretch the net between the 2 poles, and they walk up to trees, and then they slam the net down over the trees. And they are very, very good at doing that. It is very effective in Chad. The one difference that it works there quite well is that the terrain is a little bit more accessible to get to the Quelea, compared to most of the Southern African sites. And in Chad, they limit their catches to 20,000 Quelea per day, because that is how many Quelea the group of 8 can handle. So they process, defeather, etc. Quelea, and then they take the Quelea to market, also for own consumption, but mostly for selling. And they're getting, I think, 40 American cents per bird. So it can be a very, very good source of income, as well as a good source of protein. This is Professor Cheek in Tanzania, busy with establishing a big funnel net. So this funnel net trap has a light box. So the rest of the netting is on the right-hand side. So there's a light being reflected from this mirror here into the net. So late at night, people are employed to make noises, and they chase the birds into this net. And birds prefer to fly into where the light source is, because that's easier for them to see where they move. This is just different angles of the netting. So there at the back there is the collection box, and this is the poles at which the net has been suspended, and that's the rear end of the netting. So behind the tree there, from all different directions, when the Quelea have settled in the breeding colony, they start making noises, and the birds come flying into the net. Okay, one of the methods that we've also seen in Tanzania is the good old slingshot. So this is a person using the slingshot to shoot stones over the Quelea or into the trees, and that succeeds in scaring them away from that area. Okay, if we look at alternative chemicals, maybe as for use as repellents, there has been variable results on methiacarb. It's also a chemical that's banned in the European Union. Our captive studies on feeding organophosphates to Quelea has shown that once Quelea are at the starvation stage, they still eat small grains that have been sprayed with 4 times the registered dosage rate. So at maybe a small scale, maybe at the subsistence farmer level, that might be effective, because Quelea can then choose somewhere else to go or go back to the field. But in most cases, what we've seen is the Quelea actually just move on to the neighbor, and the problem is still pervasive in the homestead or in that production area. There's been mention of alpha chlorodo, so it's a narcotic agent. So this is sprayed on grains, and it is scattered for Quelea to come and feed on. Once they start noticing the grains, you can get quite a lot of different results from that. So there's a lot of Quelea that can eat that, but you have to be very, very careful, because some of the non-target birds would also come in and feed on that, and that you have to be vigilant in order to collect the Quelea and kill them before they wake up from those doses. Methyl anthranilate is a taste in food. So it provides it's like a grape flavor that is effectively used on rice to protect rice in a fumigation type of setup. So it's totally not toxic, but the drawback it's very expensive. So that's where they go for it's like a fogging, or at the very, very, very low level rate, so that the birds find it very, very revolting, that the taste of or the smell of grape, and it gives them the residues on rice, etc. is of no concern, because it's non-toxic, and it's a well-known taste additive to food. As there's been some studies on 4-aminopyridine, as well as on ammonium sulfate, also just plain aluminum sulfate, trimethacarb, Some studies have suggested that caffeine can work. It is a very, very bitter chemical, although birds do not have taste receptors per se. They do have physical effects. Caffeine can irritate the digestive tract, etc. And as I've alluded to earlier, the use of molasses or any other maybe insulating disruption chemical that is non-toxic, maybe a non-toxic surfactant, can be used when the environmental factors are right, like for instance under cold conditions. There's also a possibility that some kind of other non-toxic sticky agent can make the flight of Quelea more energy dependent. So any small changes in the metabolic energy budget of these birds might have far-reaching consequences. It reduces the vigor of the birds, and they are not able to keep up that energy budget by feeding, etc. And then one of the things is we recommend alternative screening of other chemicals for repellency. And I don't think all of the chemicals have been tested yet. So it is a good avenue to continue to look at that. So if we look at strategies, the basic practical steps that one can take is to ensure that there's good agricultural practice with good phytosanitary practices, ensure that the lands are clean without weeds, etc. Looking at agricultural practices is looking at alternative crops. In South Africa, we have, over the last 2 decades, we've seen an increase in overwintering Quelea. The practices, especially in the area called the Springbok Flats, it's about 150 kilometers north of Pretoria. It's a huge area, and it is ideal for the cultivation of small grain crops. But the farmers, they have the crop rotation they do is going from maize to winter wheat. And the Quelea realized that if they remain in an area, there is going to be food for them over the winter. So changing that practice will immediately change the behavior of the Quelea. And then one looks at, it has to be, the management of Quelea has to be totally integrated. Anything from seeding dates and planting dates and other more bird repellent cultivars. There's been studies on trap crops and different intercropping options, as well as crop rotation. And then an important thing is, in order for farmers to look at seeding dates, it will be essential to look at the prediction of Quelea breeding. So I think Dr. Dallema is the one that worked with Professor Cheek on the first Quelea breeding modeling and prediction model. And then I don't think any one technique will work for Quelea. So there has to be multiple strategies that needs to be followed. And from using repellents and bird scaring, as you'll see in the talk that's going to follow. And then also looking at the relation of drones for bird dissipation, reconnaissance, and alternative spraying. And then also looking at optimizing and minimizing the effective pesticide application as a strategy, because we can see that the pesticide is being sprayed by the aircraft at night, can travel quite a distance, and the spraying drones will at least limit that effect by spraying directly onto the trees. And then we must never forget the small-scale farmers. They are at the mercy of the Quelea, and in South Africa, it's only commercial farmers that are reliant on the Department of Agriculture to provide the Quelea control of sites, and that is only done now, at least. There's an economic threshold before the the government will intervene and organize a control operation. And then also mentioned by Professor Cheek is there could be some scope for looking at biological agents to cause zoonotic diseases in Quelea. And then wherever one has an integrated approach, this has to be community-based. So community-based integrated Quelea management should be promoted where possible. And just would like to thank our project leader and our co-workers, Professor Cheek from Natural Resources, and Dr. Sidat, Colin Mariki from Botswana, Bowes Mtebesia, and late Richard Magoma from Tanzania, John Venn and Dudley Farnham and Enoch Adrani from NRI, and then Dr. McWilliam, Peter Jones, and the late Clive Elliott, and that has been working on Quelea for decades. And in the ARC team, Piti Fenika, Joel Muka, Ezekiel Skutla, and Jan de Klerk. And I would just like to thank the FAO for the opportunity to share some of our expertise or experiences. Thank you very much.